Welcome back to the Deep Dive. This is the show where we really try to get into the weeds of the latest machine learning research, giving you, hopefully, a bit of a shortcut to, really understanding what's happening at the cutting edge. Today, we're diving into something pretty fascinating, an area that's really pushing boundaries in AI. Specifically, we're talking about situations where, well, you might have tons and tons of data, just mountains of it, but actually interacting with the real world to learn. That's either super limited, maybe way too risky, or just, impossibly slow. Just think about it for a second. How would you train an AI agent, say, to make really critical decisions in healthcare? I mean, every single mistake could have serious consequences for a patient. You can't just let it learn by trial and error there.
No, absolutely not.
Or what about autonomous driving? You can't possibly let a self-driving car learn by making endless mistakes on actual roads, can you? I mean, the potential for accidents is just,
Yeah.
it's unthinkable.
Right. These aren't environments for that kind of learn-as-you-go approach. The stakes are just way too high.
Okay, let's unpack this then. This is exactly where this field called offline reinforcement learning, or offline RL, steps in. It's a bit of a paradigm shift, really. Instead of the typical RL approach where the agent learns by constantly doing things, interacting, getting feedback live, offline RL agents learn entirely from static, pre-collected data sets. It's almost like, imagine giving a really smart student this massive textbook filled with detailed past experiences, every situation, every decision made, every outcome, and saying, okay, become an expert just from this book without ever actually trying it live.
Yeah, that's a great analogy. Learning from the data, not through fresh interaction.
Exactly. It's aiming for this super safe, data-driven way to learn complex decision-making.
And that student textbook idea, it perfectly captures the huge potential of offline RL, particularly for those, high-stakes situations you mentioned where interaction is costly or dangerous. But like any powerful new approach, it's definitely got its own set of significant technical hurdles. The two big ones that researchers are always wrestling with are called extrapolation errors and value overestimation. Let me try and break those down a bit.
Okay.
So think about our AI student, again, studying its textbook. An extrapolation error is basically when it tries to apply what it learned to a situation that looks, well, fundamentally different from anything it saw in the book.
Outside the textbook examples.
Precisely. So if our self-driving car was only trained on data from sunny, dry days and suddenly it hits, I don't know, a patch of black ice on a snowy night, something totally out of distribution, or owed, as we call it, its learned policy, might suggest actions that are just completely wrong.
This is guessing.
It's guessing. It's operating in totally uncharted territory. It's like trying to navigate a jungle using only a city map. The results, usually unpredictable and often pretty bad.
Okay, that makes sense. Extrapolation error. What about the second one? Value overestimation.
Right, value overestimation. This is where our AI student gets a bit, well, overly optimistic. In its drive to find the absolute best action, it might look at one of these unseen out-of-distribution actions and think, wow, this action I've never really seen used in this specific situation. It must be amazing. It's going to lead to huge rewards.
Like a hidden gem.
Exactly. But the problem is, without any real-world feedback to sort of ground that optimism, this belief can be totally unfounded. It's just wishful thinking based on the model's internal calculations, extrapolating perhaps incorrectly.
So it overestimates the potential payoff.
Precisely. It's like an investor looking at some totally unknown, super risky startup and being absolutely convinced it's the next big thing with no real evidence. This unfounded optimism can lead the agent completely off track, making it chase policies that aren't just suboptimal, but could actually be dangerous in the real world.
Okay, so extrapolation errors and value overestimation, the two big pitfalls. How do current methods try to deal with these?
Well, most current offline RL methods try to tackle these using various kinds of regularization. You can think of regularization as adding like intelligent guardrails or constraints to the learning process.
Keeping it on the known path.
Sort of, yeah. These guardrails try to keep the agent's behavior firmly within, or at least very close to, the patterns and actions it has seen in its training data, in its textbook.
Makes sense.
But here's the catch, the central dilemma, really. How tight do you make those guardrails? How much regularization do you apply? If you're too loose, you don't solve the extrapolation problem. If you're too tight,
You stifle it.
exactly. You stifle its ability to explore and find potentially better actions. Actions that might actually lead to higher rewards, even if they're a bit different from the textbook examples. You kill the potential for improvement beyond just mimicking the data.
So it's this trade-off.
Yeah.
Exploration versus safety, essentially.
It's a constant tightrope walk. Too conservative, and you just clone the existing behavior. Too adventurous, and you risk falling off the cliff due to those extrapolation errors.
And that tightrope walk, that fundamental dilemma, is exactly why today's deep dive is so interesting. We're looking at a really fascinating new research paper. It's titled Learning to Trust Bellman Updates, Selective State Adaptive Regularization for Offline RL. Our mission today as part of the Neural Intel podcast is to really dig into how this paper proposes a, frankly, quite novel and elegant way to get around this problem of fixed one-size-fits-all regularization. Their goal is to unlock the full potential of what are called Bellman updates. And for anyone less familiar, Bellman updates are really the absolute core of how reinforcement learning agents learn. It's how they estimate future rewards, how they figure out the long-term value of making a certain decision right now. It's fundamental to planning.
The engine of RL, really.
Exactly. And what's really exciting, and what we'll get into, are the aha moments in this paper. We'll explore how their new method dynamically adapts its level of trust in these Bellman updates. It decides how much to rely on them based on the specific situation, the quality of the data right there, right then.
Right, not just one rule for everything.
Precisely. And we'll see how this dynamic trust seems to dramatically improve not just the learning during the offline phase, but also, crucially, the transition to online performance, which is often a really tricky step. We'll be focusing, as always, on the technical details and the implications of this tech. All right, let's dive right into that core problem in offline RL, what the paper calls the fixed regularization dilemma.
Okay.
This is where things get really interesting because it's such a fundamental challenge. So the agents trained only on this static data set, right? That big textbook. We mentioned extrapolation errors. Let's revisit that. Our self-driving car, trained only in sunny California, suddenly faces a blizzard in Chicago. It's outside its training distribution.
Completely owed.
Right. So its policy, trying to figure out the best action, might suggest something. Well, something it's never seen done successfully in that specific context. Snow, ice, low visibility. It leads to unpredictable, often poor results because it's essentially flying blind.
It lacks reliable info for that novel scenario.
And then, as you said, compounding this is value overestimation. The agent gets overly optimistic about those unknown OD actions. It thinks, oh, turning sharply on this icy patch. Never seen it end well in the data, but my model predicts high reward.
Based on flawed extrapolation, yeah.
But without real-world checks, that optimism is baseless. It can lead the agent to chase these dangerous policies, like that investor pouring money into a totally unproven venture. Now, the paper points out two main ways current methods try to fix this. First, value regularization methods. The big example here is conservative Q-learning, or CQL. What does CQL do?
Right, CQL is quite clever. It basically works by actively suppressing the Q values, the estimated quality or future rewards specifically for those out-of-distribution actions.
Pushing their estimated value down.
Exactly. It essentially forces the agent to be pessimistic about actions it hasn't seen good evidence for in the data set. It says, look, if you haven't seen this action work well in this state before, assume it's probably bad. Be conservative.
Okay, so that's value regularization. What's the other main approach?
The second category is policy constraint methods. A well-known example is TD3 plus BC. Now, unlike CQL, which messes with the Q values, TD3 plus BC works differently. It directly restricts the agent's policy the way it chooses actions, forcing it to stay very, very close to the actions that are actually found in the original data set.
So it kind of anchors the policy to the data.
Yeah, you can think of it like putting a strong leash on the policy, pulling it back towards the known safe actions from the training data. It says, don't stray too far from what's in the textbook.
Got it. So value methods push down unknown values. Policy methods keep the actions close to known ones.
Precisely. And the key thing for both these approaches, CQL and TD3 plus BC, is that they achieve this using some form of regularization term added to their learning objective. These terms fundamentally make the learning process more pessimistic, more conservative. They prioritize safety and staying close to the data over potentially risky exploration.
Which makes sense, given the dangers of extrapolation. But that leads us straight back to the dilemma of fixed regularization strength, right?
Exactly. That's the core issue this paper tackles. While some regularization is clearly needed, the common practice of using a single, fixed, global regularization coefficient, one setting applied everywhere, all the time, is deeply problematic.
Why is one fixed number such a bad idea?
Well, think about it. If that fixed coefficient is set too weak, It just doesn't do enough. It fails to properly address the extrapolation errors and that value overestimation problem we keep talking about.
So the agent still wanders off.
Yeah, the policy might still drift into unreliable territory, make those risky OD decisions, and perform poorly or unstably when you actually try to use it. It's like trying to train a gymnast with super loose safety ropes. They
Yeah.
might try crazy stuff that just doesn't work.
Okay, so too weak is bad. What if it's too strong?
If it's too strong, it pushes the learning too much towards just behavior cloning. The agent essentially learns only to mimic the actions exactly as they appear in the dataset.
Like rote memorization.
Exactly like rote memorization. Our student just memorizes the textbook answers without understanding the why or figuring out if there's a better way. Now, this seems safe, right? It stops dangerous new actions. But it fundamentally cripples the agent's ability to leverage the real power of those Bellman updates.
Because Bellman updates are about finding better ways.
Precisely. They allow the agent to potentially discover novel sequences of actions that lead to higher long-term rewards, to actually improve beyond just copying the data. Too much regularization kills that potential for innovation and optimization. It traps the agent into just reproducing the past, not discovering a better future.
That's a really clear explanation of the dilemma.
And the paper highlights 3 key reasons why a single, fixed global coefficient struggles so much. First, there's task-level variability.
Different tasks need different levels of caution.
Absolutely. Training a drone for a complex search and rescue mission in treacherous terrain probably needs very strong regularization, high stakes, need for extreme safety. But training a drone for a simple, predictable package delivery route, maybe you want more flexibility to find efficient paths, so less regularization might be better. A single setting can't be optimal for both.
Makes sense. What's the second reason?
Second is the training dynamics. Ideally, the amount of regularization shouldn't even be static during training for a single task. Early on, when the policy is still kind of random and unreliable.
You want trait constraints.
Definitely. Keep it from doing crazy things. But as training progresses and the policy gets better, more aligned with the reliable data, well, maybe you want to loosen the reins a bit.
Let it explore more safely.
Exactly. Allow it to trust its own learned Bellman updates more. Give it freedom to optimize without being overly constrained. A fixed coefficient can't adapt to this learning journey.
Okay, task variability, training dynamics. What's the third?
The third is data density variability. This one's pretty intuitive. Imagine parts of your state space where you have tons of really good, reliable data points.
You should trust the learning there more.
Right. You'd want to trust the Bellman updates more in those dense, high-quality regions, meaning you'd want less regularization there. Let the agent learn and optimize freely. But now imagine areas where the data is sparse, maybe noisy, maybe contradictory.
You need to be much more cautious.
Much more cautious. You'd want stricter constraints, more regularization, forcing the agent to be conservative and stick closer to whatever little reliable data you have.
So the ideal regularization level changes based on the task, the training stage, and even the specific state you're in.
Precisely. But despite all these nuances, what do existing methods usually do? They make you go through tons of manual trial and error, endless hyperparameter tuning, just to find one fixed global coefficient that's hopefully a decent compromise.
Which sounds incredibly inefficient.
It is. It's hugely inefficient, time-consuming, and as this paper shows experimentally, it's often suboptimal. You leave a lot of potential performance untapped.
And this fixed regularization doesn't just hurt the offline learning part, right? You mentioned it causes problems for the offline to online or O2O transition too.
Big problems, yeah. That O2O phase is critical, taking the offline trained policy and fine-tuning it in the real live environment.
Where the AI actually needs to perform.
Exactly. And that fixed regularization strength really throws a wrench in the works here. If you used a low coefficient offline to try and get better performance, well, your policy might be poorly initialized, maybe unstable because it learned some bad habits from those extrapolation errors.
Not ready for prime time.
Not ready. It's like launching a rocket with a shaky navigation system. But if you went the other way, use a really high coefficient for safety.
It creates other issues.
Yes, it can create these big mismatches when you switch to online. For value methods like CQL, you can get a huge sudden jump between the pessimistic offline Q values and the more optimistic online estimates. It destabilizes learning.
And for policy constraint methods.
For things like TD3 plus BC, a high offline constraint can cause a major misalignment between the learned policy and what the critic network suggests is optimal online. Again, instability. It makes smooth, efficient fine-tuning really difficult.
So existing fixes, like maybe gradually reducing the constraint online, still suffer because they started with that single fixed value.
We're often limited by that initial fixed setting, yeah. It's a fundamental bottleneck for deploying truly adaptable AI systems that can learn offline and then transition smoothly to the real world.
Okay, this sets the stage perfectly for the paper's solution. Selective state adaptive regularization, or SR. How does it tackle this dilemma?
SR's approach is really elegant. It directly confronts this dilemma not by picking one fixed level, but by dynamically figuring out how reliable the Bellman updates are in any given situation.
So it's not one rule for all states.
Exactly. Instead of that global coefficient, SR aims to guide the policy by deciding how much to trust those potentially optimistic Bellman outcomes at the state level.
Like a smart advisor whispering in the agent's ear.
That's a good way to put it. In states where the data seems shaky or sparse, the advisor says, be careful, stick to what you know. But in states with lots of good data, it says, okay, here you can probably trust your calculations. Feel free to optimize a bit more. It's this dynamic, context-aware guidance.
That sounds like a much smarter way to handle it. How does it actually do that? What are the key technical bits?
There are three core components that make SR work. First, as you alluded to, are the state adaptive regularization coefficients.
So not one beta, but a beta for each state S.
Precisely. Instead of a single fixed number, SR uses a neural network to generate a unique coefficient, let's call it beta, for every single state S the agent encounters.
Wow, okay.
This allows the regularization strength to automatically adjust on the fly based on the context of that specific state. It reflects how trustworthy the Bellman updates seem to be right there. It's like having a custom-tuned safety setting for every possible situation.
That's component one, state adaptive coefficients. What's next?
Second, and this is a really insightful part of the paper, they establish this powerful connection between mainstream offline RL approaches. They basically prove, mathematically, that a method like CQL, value regularization, is fundamentally equivalent to policy constraint methods like TD3 plus BC.
Cool equivalent, how they seem different.
It's subtle but fascinating. They show that the mechanism in CQL that makes it pessimistic about unseen actions that log some expo term ultimately has the same effect as directly controlling the probability of the agent taking actions that are already in the dataset.
Okay, wait. So pushing down Q values for unknown actions has the same net effect as forcing the policy to stick to known actions.
At a fundamental level, yes. Both approaches end up influencing how likely the learned policy is to choose actions it's already seen evidence for in the training data. This equivalence is huge because it means SR can use its state-adaptive mechanism universally.
So the same beta S can work for both CQL style and TD3 plus BC style methods.
Exactly. It provides a unified framework, making SR broadly applicable without needing totally different designs for each type of algorithm. It's like discovering a master key.
Very clever. Okay, state adaptive coefficients, unified framework. What's the third piece?
The third component is the selective regularization method. The researchers realized that even with adaptive coefficients, you might still have some low quality or just plain bad actions within the data set itself.
Right, the textbook isn't perfect.
Exactly. Even if the adaptive coefficient for a state says relax, if the only examples for that state lead to poor outcomes, the policy might still learn to favor those bad actions. So SR adds another layer of intelligence. It focuses the regularization only on a carefully selected subset of high-quality actions from the data. It creates a sub-dataset, let's call it D hat, containing only the really good examples.
Filtering out the junk.
Essentially, yes. By only applying the adaptive constraints based on this high-quality D hat, it stops the policy from being pulled towards bad examples that might exist in the full dataset. It learns from the best, not just from everything available.
Okay, that makes a lot of sense. Focus on the good stuff.
And these three pieces, the adaptive coefficients, the unified framework, and the selective regularization, they all work together.
Creating a more intelligent learning process.
Right. By adapting trust state by state, applying it universally, and focusing on quality data, SR bridges that offline to online gap much more effectively. They show it enables efficient O2O fine-tuning using just simple, linear coefficient annealing.
Meaning the transition becomes smoother.
Much smoother, more stable, and more effective. It's a big step towards making these powerful offline RL methods truly practical.
All right, let's dive even deeper now. How exactly do these state adaptive coefficients work? You said a neural network generates them.
Yes, that's right. Instead of picking one global beta, There's a separate network, let's call it the beta network, that takes the current state S as input and outputs the specific regularization coefficient beta for that state.
And this allows it to adjust automatically.
Exactly. It can adapt to different tasks because the network will learn different mappings from states to coefficients depending on the overall task structure and data distribution. And it adapts during training. As the main policy and value networks evolve, the beta network also updates.
How did it know what the right coefficient for a state is? What's it basing that decision on?
It leverages what the paper calls Bellman-driven results. Essentially, it looks at how consistent and reliable the Bellman updates seem to be for that state, which is closely related to the data density information available there.
So if the Bellman updates look solid because there's good data,
then the beta network can learn to output lower beta S, relaxing the constraint, allowing the policy to trust its own learning more and explore.
and if the data is sparse or the updates seem inconsistent,
It learns to output a higher beta, tightening the constraint, forcing the policy to be more conservative and stick closer to the known data for safety. It's like an intelligent thermostat adjusting based on the perceived reliability of the information.
okay. And you mentioned that unified framework, the equivalence between CQL and policy constraints.
Yeah.
How do they formalize that?
Yeah, this was a key insight. They showed mathematically that the regularizer in CQL, which tries to keep Q values for dataset actions high relative to other actions, effectively penalizes the policy if the probability of taking those dataset actions, log pi, becomes too low.
So it implicitly pushes the policy towards dataset actions.
Right, and policy constraint methods like TD3 plus BC do that explicitly. They directly add a term that encourages log pi for dataset actions to be high. The paper showed these achieve fundamentally the same goal, influencing the probability of dataset actions.
Which means the same adaptive beta coefficient can control either mechanism.
Precisely. It simplifies things enormously.
How does the beta network actually trained? What tells it whether to increase or decrease beta?
It has its own objective function. Without getting too deep into the equations, it basically looks at the discrepancy between how likely the current policy pi is to take a dataset action A in state S, that log pi S term, and a dynamically calculated state-level threshold.
A threshold, like a target confidence level.
Kind of. Think of this threshold as defining a trust region or a comfort zone for the policy at that state. This threshold itself is cleverly calculated based on the policy's own statistics, its mean and standard deviation at that state, and it's controlled by another parameter, let's call it n, which sets the width of this trust region.
Okay, so there's a target region. What happens then?
If the policy's probability for dataset actions, log pi, is higher than this threshold, meaning it's confidently doing things consistent with the good data, the objective function encourages the beta network to decrease beta S for that state, relax the constraints.
Trust the policy more.
Right. But if log pi falls below the threshold, maybe the policy is struggling or trying to deviate too much, the objective encourages the beta network to increase beta, tighten the constraints, be more cautious.
It's a self-regulating feedback loop, adapting the caution level state by state based on how well the policy aligns with the trusted data region.
Exactly. It creates this really flexible, state-specific balance between safety and exploration.
But wait, you mentioned that threshold depends on a parameter n that controls the width of the trust region. If n is fixed, aren't we back to a similar problem as a fixed beta?
Ah, excellent point. Yes, a fixed n would still be suboptimal across different tasks or training stages. The paper anticipated this. They introduced distribution-aware thresholds.
So n adapts too.
It adapts too, but in a simpler way. It doesn't need a whole separate network. Instead, it uses a schedule. It starts low, let's say n start, early in training when the policy is unreliable. This keeps the initial trust region small and ensures enough constraint.
Like giving a learner driver a small practice area.
Perfect analogy. Then, as training progresses, n gradually increases linearly towards a maximum value, nend. This widens the trust region, allowing more exploration as the policy gets better.
Does it increase forever?
No, the increase cleverly stops once the policy is deemed sufficiently close to the dataset distribution. This ensures the trust region evolves with the policy's capability, only becoming more permissive as the policy itself becomes more reliable. It's a very neat way to guide the learning.
Okay, adaptive coefficients, adaptive trust region widths. Now, what about that selective regularization part, focusing on high-quality actions?
Right, so even with all this adaptive machinery, there's still the potential issue of bad examples within the dataset itself messing things up.
The imperfect textbook problem again.
Exactly.
Yeah.
So the idea of selective regularization is to build that filtered subdataset, D hat, containing only trajectories whose total return is above some threshold GT. Basically, filter for the successful runs.
And then apply the adaptive regularization only using this D hat.
That's the core idea. By focusing the constraints, even the adaptive ones, only on these proven high-quality examples, you prevent the policy from being dragged down or misled by suboptimal actions that might be present in the rest of the data.
But you mentioned there were two scenarios depending on the data set.
Yes, this is important. For datasets with low-quality variance, where most of the data is pretty good and consistent, using just the high-return D hat for regularization works well. The few lower-quality actions outside D hat can just have their values updated naturally by Bellman backups without being artificially constrained.
Okay, what about the other case? High variance data.
For datasets with high-quality variance, think messy replay buffers with a mix of good, bad, and mediocre attempts, like the medium replay datasets in D4RL just using the high-return D hat, can actually be bad.
Why?
Because those high-return trajectories might only cover a very small, specific part of the state space. If you only apply constraints there, you leave vast regions of the state space completely unconstrained by the regularization type.
Leading to overestimation in those unconstrained areas.
Exactly. The policy might become wildly optimistic about actions in states that weren't part of the high-return D hat, simply because there's no regularization holding it back there.
So how do they fix that for these messy data sets?
They use a different, more sophisticated filtering approach inspired by a method called IQL, implicit Q learning. It's clever. They first pre-train Q networks and a value network, V network. The V network estimates the average value of just being in a state S.
Okay.
Then, instead of filtering whole trajectories, they filter individual actions within states. They select an action A in state S for their quality subdataset if its Q value, QSA, is greater than the average value of the state V.
So selecting actions that are better than the average for that specific state.
Precisely. This captures the relative value or advantage of an action in its specific context. This IQL-style filtering results in a subdataset that's still high quality but covers a much broader range of states compared to just picking top trajectories.
Because good actions can happen even in trajectories that weren't optimal overall.
Exactly. This ensures that pretty much all states have at least one action included in the regularization process, preventing those large, unconstrained regions and the associated overestimation. It's a much more robust way to handle diverse, heterogeneous data.
That IQL-style filtering sounds crucial for real-world data.
It really is. It refines the policy's focus intelligently, making it more robust, even when the initial data is far from perfect.
And you mentioned they even extended this to deterministic policies like TD3 plus BC. How do they handle the probability bias part there?
Yeah, that was neat. Since a deterministic policy outputs a single action, not a probability distribution, log pi isn't directly applicable.
Right.
So they used a clever trick. TD3 typically adds some noise, often Gaussian noise with a standard deviation delta, to the policy's output for exploration. They essentially treated this fixed exploration noise delta as the standard deviation of a pseudo-distribution around the deterministic action.
Ah, so they create a sort of artificial probability distribution.
Exactly. It allows them to calculate a pseudo-log pi based on how far a dataset action is from the policy's deterministic output, using delta as the scale. This lets the whole state-adaptive coefficient logic plug right in, even for deterministic policies.
Showing the versatility of the core SR idea.
Definitely. It makes the adaptive regularization framework remarkably general.
Okay, that's a fantastic breakdown of how SR works. Now let's shift back to the practical payoff, especially for that critical offline to online O2O transition.
Right. This is where SR really shines, potentially. The goal is to take that policy learned safely offline and then efficiently fine-tune it in the live environment.
Making it adapt to the real world quickly and safely.
Exactly. And remember how we framed those state-adaptive coefficients beta as representing the policy's confidence or trust in its Bellman updates for state S?
Yeah, low beta means high trust, high beta means low trust. Be cautious.
Precisely. This dynamic trust level inherently bridges the gap between offline and online learning. When beta is low, high trust, the update is more optimistic, more exploratory, looking more like a standard online RL update. When beta is high, low trust, it's constrained, conservative, sticking closer to the offline data.
So the learning mechanism itself smoothly varies between conservative and exploratory based on the state.
Yes, which minimizes those jarring discrepancies that plague fixed regularization methods when they suddenly switch from offline pessimism to online optimism. SR is already operating on a spectrum.
How do they handle the coefficients during the online phase then? Do they keep adapting?
Actually, the proposed mechanism is remarkably simple, just linear annealing. They take the final beta values learned by the beta network offline, and during the online fine-tuning steps, they simply decay these coefficients linearly towards zero.
So gradually removing the regularization constraints as the agent interacts more with the real world.
Exactly. It allows the agent to progressively become more reliant on the new, real-time online experience, shedding the offline conservatism as it gathers fresh data and gains confidence in the live environment.
How does this compare to what other O2O methods do? You mentioned issues like sudden Q value increase.
Right. Many older methods, especially those based on heavy value pessimism like some forms of CQL, can suffer badly here. They might have learned very low Q values for owed actions offline. Then online, they encounter a new state action pair, get a positive reward, and suddenly the Q value jumps dramatically. This can cause instability and performance drops.
Because the value landscape changes too abruptly.
Exactly. SR avoids this because its state adaptive nature prevents that extreme underestimation offline. The pessimism was already tailored state by state. So when it goes online in the betas anneal, the Q values shift much more gradually and stably.
That sounds much more robust.
It should be. Another huge advantage they highlight is the reduced reliance on the original offline dataset during the online phase.
How so?
Because that beta network was trained so thoroughly offline to adapt its coefficients across many states, it learns a degree of generalizability. It can often produce reasonable beta values even for new states encountered online that weren't in the original dataset.
So the adaptability itself generalizes.
That's the idea. This means you might not need to keep the entire massive offline dataset around during online fine-tuning just to keep applying the constraints.
Which could be a huge practical win. Storage, privacy.
Absolutely. You might only need a small buffer of recent online experience, maybe initialized with a few high-quality trajectories from the offline set, or potentially discard the offline data entirely after the initial training. This contrasts sharply with some unified O2O methods that require the offline data throughout the online phase to maintain stability, which can be impractical.
Okay, so summing up the O2O benefits.
Yeah.
More stable fine-tuning, more efficient online exploration, because the constraints adapt and fade intelligently, and potentially much lower data dependency during deployment.
Those are the key advantages SR aims for in the O2O setting: reduced offline mind mismatch and better data efficiency.
All right, the theory sounds incredibly promising, but does it actually work in practice? Let's talk about the empirical validation. What did the experiments show? They used the D4RL benchmark, right?
Yes, D4RL is the standard playing field for this kind of research. It has tasks like Mujoko, locomotion, half-cheetah, hopper, walker, and the tricky ant maze navigation tasks. And crucially, the data sets vary a lot in quality, from expert data to medium quality and those messy medium replay buffers we talked about.
And they plugged SR into CQL and TD3 plus BC.
Correct. They created SR-enhanced versions, let's call them CQLSA and TD3 plus BCSA, and compared them against the original baselines.
So how did they do purely in the offline setting, learning just from the static data?
The results were pretty striking looking at Table 1 in the paper. SR consistently and often significantly outperformed both standard CQL and standard TD3 plus BC across almost all the datasets tested.
Significant improvements, like what?
Well, the gains were especially noticeable on those tougher, lower quality datasets. On Hopper Medium V2, for instance, which is known to be challenging, TD3 plus BCSA scored around 101.6, while the baseline TD3 plus BC was only at 58.7. That's almost double the performance.
Wow, that's a huge jump. Why is such a big difference?
The paper attributes it mainly to two things: SR's ability to selectively focus on the valuable parts of the data using that D-hat subdataset, filtering out the noise. And second, the enhanced generalization that comes from trusting Bellman updates more effectively in reliable states thanks to the state adaptive coefficients.
So it's both smarter filtering and smarter learning.
That's the idea. They did add a small behavior cloning term for stability on the really complex ant maze tasks, which is a common practice, but the core gains came from the SR components.
Okay, strong offline results. What about the offline to online OTO performance? How did it compare when fine-tuning online?
For the O2O tests, they typically allowed 250,000 steps of online interaction after the offline training phase. They compared SR against the baselines, CQL, TD3 plus BC, and also against several other methods specifically designed for O2O, like IQL, SPOT, and FAMO2O.
And how did SR fare in that comparison?
The results shown in Table 2 indicate that SR achieves very competitive performance, often outperforming the other methods, especially we're looking at CQL-SA and TD3 plus BC-SA.
So it transitions well.
It seems to transition very effectively. The reasoning goes back to what we discussed. Those adaptive constraints learned offline reduce that initial shock or mismatch when going online. This allows for more stable and efficient exploration and learning during the fine-tuning phase. It builds that smoother bridge.
The experiments seem to really back up the theoretical advantages. Did they do any ablation studies to isolate the impact of different SR components?
Yes, they did, and the ablations provide some really crucial insights. They're essential for understanding why it works.
What did they find about the state adaptive coefficients? Were they really necessary?
Absolutely necessary. When they replaced the state adaptive beta with the best fixed global beta they could find through tuning, performance dropped significantly. The fixed beta kept the policy trapped, unable to improve much beyond the dataset level.
Because it couldn't selectively trust Bellman updates.
Exactly. The state adaptive coefficients, in contrast, allowed the policy update to expand into reliable regions identified by Bellman updates, enabling performance that actually surpassed the dataset baseline. It showed the power of dynamic state-level adaptation.
Okay, so the adaptive betas are key. What about the selective regularization part? How important was how they selected that high-quality subdataset D had?
This was also very revealing, especially on those messy, high-variance datasets like Hopper Medium Replay V2, when they used the simpler method of just selecting entire trajectories with high returns.
Performance wasn't great.
Performance actually degraded sometimes, because, as we theorized, that high-return D-hat was too sparse, leaving large parts of the state space unconstrained, leading to overestimation issues.
And the IQL style filtering.
The IQL style approach, selecting actions based on their advantage, QS, worked much better. It created a broader, more representative, high-quality sub-dataset that provided better coverage. This prevented the overestimation problems and led to much more stable and higher performance.
Highlighting the importance of how you select quality data, not just that you select it.
Precisely. It shows the nuance needed for dealing with realistic, heterogeneous data. They also briefly looked at computational cost effect. SR adds a bit of overhead with the beta network and potentially the IQL pre-training, but the significant performance gains seem to justify it.
Okay, let's try and wrap this up. We've covered a lot of ground. We started with the core challenge in offline RL, that fixed regularization dilemma, forcing this awkward trade-off between safety and learning potential.
Right, the one-size-fits-all problem.
And SR comes in with this really clever solution, dynamically adjusting the agent's trust in its own learning process, the Bellman updates, on a state-by-state basis.
Using those state adaptive coefficients.
Exactly. And powered by key innovations like establishing that equivalence between value and policy methods, allowing a unified framework.
And that crucial selective regularization, focusing on high-quality data, especially using the IQL-style approach for messy datasets.
It all comes together to offer, based on the results, much more robust offline learning and, critically, a much smoother, more efficient transition to online fine-tuning, potentially needing less reliance on the original dataset.
Which has huge practical implications for actually deploying these agents in the real world.
So, stepping back, what's the bigger significance of this work? What does it mean for AI development?
Well, I think it means we're making real progress towards RL agents that are more flexible, more adaptable, and ultimately more trustworthy. Agents that can learn effectively from the kind of imperfect, static data we often have available.
Real-world data.
Real-world data. And then seamlessly transition to interacting with the actual environment and continue improving safely and efficiently. This kind of work is crucial for building AI systems that are not just powerful in simulation, but also robust and reliable enough for critical applications, healthcare, robotics, autonomous systems, you name it. It's about moving towards more nuanced, intelligent control within AI.
That's a great summary. And maybe a final thought for you, our listeners, to ponder this idea of dynamically adjusting trust based on context and data quality. Where else could that be applied? Beyond just RL action selection, think about other complex AI systems where the quality or reliability of information varies. How could this kind of fine-grained adaptive control, rather than broad assumptions, unlock more potential? It suggests a move towards AI that's more aware of its own uncertainties and can adapt its strategies accordingly. A fascinating direction. To stay updated on the latest AI and ML research papers like the one we discussed today, remember to visit our webpage. The link is in the bio. Thanks for joining us on the deep dive, and we'll catch you next time.